So as we move into reaction mechanism 8, I'm going to do a little reflection on the reaction mechanisms we've done before, because this is an important sort of shifting gears point where we start doing a different kind of mechanism. So again, reaction mechanisms 2 and 3, we dealt with carbonyl containing compounds that had good leaving groups. So again, if we have a carbonyl containing compound that has a good leaving group, the chemistry that can happen is nucleophilic attack, generation of a tetrahedral intermediate, decomposition of that tetrahedral intermediate with departure of the leaving group, and in essence, we replace the leaving group with the incoming nucleophile. So we call this nucleophilic addition-elimination chemistry. We also dealt with carbonyl-containing compounds that had poor leaving groups. In that case, it was our aldehydes and our ketones. And in this case, when we have nucleophilic attack and we generate a tetrahedral intermediate, without there being a good leaving group, the only option is to protonate that resulting tetrahedral intermediate and generate an alcohol. So that's the nucleophilic addition chemistry that we saw in reaction mechanisms 4 and 5 to give us our hemiacetals and our hemiketals. And then because we had nucleophiles that contained lone pairs, we had the subsequent elimination chemistry that allowed us to generate our acetals and our ketals. So the chemistry that we're moving on to now is to consider when we have a carbonyl containing compound, where we're going to consider the acidity of the alpha carbon. So again, this is the alpha carbon because it is the carbon immediately adjacent to the carbonyl. So we're going to consider the acidity of this. And again, we don't generally consider carbon-hydrogen bonds being acidic, but the next slide here is going to highlight, well, how do you or how can you consider whether or not a hydrogen atom is acidic? And so anytime you want to consider whether a hydrogen atom is acidic, what you want to do is deprotonate the molecule, look at the conjugate base, and if there's some means of stabilizing that negative charge on that conjugate base, maybe it's resonance, maybe it's inductive electron withdrawal, that is going to help increase the acidity of that molecule. So again, stronger acids are going to generate weak and stable conjugate bases, meaning that they're happy being without their proton. The equilibrium is going to lie on the side of the conjugate base because that negatively charged species is stabilized in some way. And again, just to highlight, we're not saying that hydrogen atoms on carbons are generally acidic, like we think of protons on carboxylic acids, but they are significantly more acidic than any other carbon-hydrogen bond in this context. So to just kind of draw out what we mean here, so again, we're going to have a carbonyl-containing compound, and we are going to be looking at chemistry at the alpha carbon. So the chemistry really is to consider deprotonation of this carbonyl or this hydrogen on this alpha carbon. We're going to generate, initially, if you wanted to think about it this way, we're going to generate a carbanion intermediate. But these electrons can easily be stabilized throughout this carbonyl. Oops, and I just drew the wrong arrows there. I was going to highlight, we need to make sure that we use the right kind of arrows here, which are resonance arrows here. And we generate, in this case, an enolate ion as our intermediate, our prime there. So this is an enolate ion. And this is, again, resonance stabilized. And this is actually on the right side here. This is the preferred form of this resonance structure because we've put the negative charge on the more electronegative atom. So it's actually preferable to generate this resonance species as compared to this species. So this one will, again, predominate, but sometimes we're going to see that chemistry will happen with the carbon atom acting more in a nucleophilic capacity. And that is going to be, again, dictated by the product that I give you, so you kind of know the direction that you're going to go. All right, so on to the mechanism, right? The goal in this mechanism is to get to an ene-diol intermediate. When students generally see this mechanism at the outset, they sort of feel like, oh, going between an aldehyde and a ketone, that has to be some redox chemistry or something fancy going on. Or if I have an aldehyde that I'm going to be adding another alkyl group to, I need to have, you know, some type of a Grignard reagent or something like that. No, none of that chemistry really happens here. What we're really doing is we are walking and migrating a carbonyl between two different carbon atoms. So when we draw this mechanism out, hopefully that will make sense. So again, we're going to start here with an alpha hydroxyaldehyde. And we're going to notice that this is a little bit different than the molecule I showed on the previous slide where we were just talking about the acidity at the alpha carbon. This is an alpha hydroxy position. And what's really going to happen here is we're going to migrate where that carbonyl is. So that carbonyl is starting out at this position, and we're going to make it be a carbon-oxygen double bond, a carbonyl, at that position. So again, this is an alpha hydroxy aldehyde. And so we're going to have this acidity of our alpha carbon's hydrogen. And for right now, I'm going to push these electrons all the way through to the most stable atom there, putting it on the more electronegative oxygen. And we generate this enolate intermediate. So again, this is an enolate intermediate. And we're going to protonate this guy, and we're going to end up with an enediol intermediate. I'll talk about that guy in just a second here. So we generate an enediol intermediate. So a couple of things just to highlight here, right? This is called an enediol. The ene referring to the alkene functional group, the diol referring to the fact that we've got two OH groups. So just to kind of orient you big picture with what's happening, we deprotonated here to generate this enolate, protonated to get this enediol, and what we're going to do now is we're going to deprotonate at this position, essentially generating another enolate, but now with a negative charge on this carbon's oxygen. And then we'll take one more step back, and then we'll reprotonate that enolate intermediate to get back to a carbonyl containing compound. But now we've moved the position of where that carbonyl group is. So let's walk through that mechanism here and see if that makes sense. So again, we should start here. I wanted to show that we're going to have base is going to come and grab this hydrogen, putting those electrons back on that carbon. So we've generated another enolate intermediate. So again, an enolate intermediate here, but importantly, we have another enolate intermediate there. And now we're going to protonate this enolate intermediate by reforming this carbonyl. These pi electrons are going to come back out here, grab that proton. And this mechanism is long enough that I have to actually go down here to show our final product. Again, we're putting our carbonyl now one position away. And we generate an alpha hydroxy ketone. So again, to highlight, really what happens is we have these two adjacent carbon atoms that are going to swap who has the alcohol group and who has the carbonyl. And we're able to do that by going through a common enediol intermediate. Now again, if we deprotonated this alcohol group, we would just go right back towards our starting molecule. But by choosing to deprotonate a different OH group, we move this in the direction of having that second carbon be our carbonyl, and then what was an aldehyde now is an alcohol. And so context for this really important kind of application is sugars generally come in two flavors. We've got an aldose and a ketose flavor. This really isn't going to become applicable until we get to chapter 8 and study carbohydrates, but again, we're going to see this mechanism come up. And again, this depends on whether the carbonyl is found on carbon 1, meaning we have an aldehyde containing sugar, Or C2, we have a ketone containing sugar. So again, as is shown with this mechanism, it's possible to interconvert or walk the carbonyl between these two positions, and that's exactly what happens when we study glycolysis. We're actually not going to study glycolysis until we get to Biochem 2, but we're going to interconvert glucose 6-phosphate, which is an aldose sugar, with fructose 6-phosphate, which is a ketose sugar. So just kind of when I was highlighting here, which OH group we take the hydrogen off determines whether we go back towards our aldehyde or forwards towards our ketone. If this was done in solution, there really wouldn't be a strong preference one way or the other, and we'd probably end up with about a 50-50 mixture of each of these. Now, when we consider enzyme chemistry, enzymes, and when we learn about enzymes and enzyme active sites, have very specific abilities to imply not only stereochemistry, but regiochemistry to reactions. And so we can selectively pull off this OH's hydrogen so that we can move from our aldehyde to a ketone if we want to move the enzymatic reaction in that direction. So again, hopefully you'll look at this reaction mechanism and recognize that we are shifting gears again, but keep that in mind as to, I tend to group these reaction mechanisms, and very seldomly will you see one that's just kind of by itself. So as you look towards reaction mechanism 9, see if you can recognize the pattern.